Gauss's law in general. Now I would like to explain the expression of Gauss's law and the mathematical calculation. And also I want to write the conditions that we have to respect in order to use this law. Let me explain all these points by the application. You know that the objects we choose uh, must be highly symmetric charge distribution, like a sphere, like a line in the plane. We talked about these objects in the last videos. Now I want to take a simple example like a sphere. This sphere is positively charged, plus. This sphere emits an electric field in all directions. E. And you see well that the emitted electric field is symmetrically distributed. First of all, in order to use Gauss's law, we have to choose one, the Gauss's surface. This surface depends on the shape of the object. Let me take this object as a sphere. I will choose a spherical Gaussian surface. In this case, for the next application, we will see which surface can we use. So in this case, the Gauss's surface is a sphere of radius r. Okay. You see here that point 2, Q is inside the sphere. We can say inside Gauss's surface. It's important, this point. Okay. Okay. What are the conditions we have to respect about this surface? First of all, it's important to write these conditions when you solve any problem. A, the electric field must be parallel to the area on the sphere. What I mean? We can take a small element of this surface. We have here the surface, and we can take any small element. We can take, for example, here, this small element. This element has area as magnitude equal dA. And you know, as vector, dA is perpendicular to this area, to this small area. Here we have dA vector. We can draw this one in the blue to distinguish between Okay, here we have dA, and here we have E. You see here at this point E and dA are parallel, okay, and the angle between them equal to 0. Any other point, we can take the point another dA. Here we have a small dA. dA vector is perpendicular to this plane, dA, and here at this point you see that the electric field is like this, and so on. Okay, so this surface must respect this point, that E must be parallel to dA. The second point, E must be radial. As you see in each line of E, path along the radius of the circle, of the sphere. Here we have at this point also radial, radial, radial. Any point must be radial in all the direction. Okay, this is the second point. The point C, E must be constant as magnitude. You see here the distance between any point here and the center. We can take a point A, here a point B, we point C, and so on the surface of Gauss's on the surface. OA equal OB equal OC, so the electric field as a point A equal EB equal EC. So we can say here EA equal EB equal EC, and so on. Be careful, EA vector doesn't equal to EB vector because they have a different direction. Okay, this is a very important point. Now I write all the conditions that it's important to write these conditions when we want to solve any problem. Before, if you want to write or if you want to choose Gauss's surface, you have to say bisymmetric. You have to write these conditions each time you want to solve any problem by using Gauss's law. Okay, let me write the expression of Gauss's law. The expression, in general, we have to relate the flux, the electric field flux phi, and the internal quantity of charge Q, Qn. In this case, you have Q inside the Gauss's surface. We can say in this case Qn equal Q. Maybe you have another cases that Qn is different of Q. We can talk about this later. What is the relation between these two quantities? We can say phi E. You know, here we must use phi equal integral EdA, because the vector E is not constant at any point on the plane of the surface. In this case, we have to use this equation. Must be equal to Q inside divided epsilon 0. It's a given quantity, constant. this is a general expression of Gauss's law. It's important to understand each point, its term, the meaning of each term. Here we have the first part, this one, and the second part, Qn and epsilon. Flux equal the integral of E dot dA. This term concerns Gauss's surface. Okay? I mean, E is calculated at the surface. dA is a area vector of this surface. And when we calculate the electric field, this field is calculated at the surface of this one, and equal Qn concerns only the charge inside the surface. Okay, only this one, and this term concern only this one. It's important, this point, because when we want to substitute each value, you have to know which value you want to use. Okay, we can do some application to understand well all these points in the next video. Thank you.